And now the whole world is talking about biodegradable and bio-based plastics, which are supposed to be recycled back into the circular economy after their use. But what about the biodegradability of plastics? Thomas Kegi, member of the board of Carbotech AG from Zurich and Basel, looks at life cycle assessment and the impact of biopolymers on the environment. So the question, Peter, is why are LCA analysis so costly and essential?
Yes, LCA analyses are always very detailed, and it is a very careful work that takes a lot of time and patience. When it is done, the study can be overwhelming, and it's essential to check very carefully each single step to improve the whole process. In this respect, I have a nice story to tell. Some months ago, I had a meeting with a senior specialist for agricultural technologies. He mentioned to me that they changed the transport of the yeast from the field to the yarn, from tractors to trucks with biodiesel engines. Mm-hmm. And this changement was a major improvement of the CO2 balance. So that means all these little changements give, in the end, a big changement in the analysis. Mm-hmm. That's why knowledge is always good. Even if the actual situation may not be the best in your case, there is always room for improvement.
Yes, I agree. I can imagine that. Thank you very much for your assessment, Peter. And now I would like to welcome Thomas Kegi from Carbotech AG with his presentation on the topic Biopolymers, Plastic of the Future, How Environmentally Friendly Are Bioplastics? Roll the film.
Welcome to my presentation about biopolymers. Are these the plastic of the future, or how environmentally friendly are these bioplastics? I first like to talk a little bit about LCA theory, about life cycle thinking, how is an LCA done, and then I'd like to show you some results about biopolymers, about the benefit of the renewability and the benefit of the degradation of those biopolymers. And in the end, I'd like to show you a comparison of biopolymers and the benefit of recycling. And then I'll end with the conclusions. Well, if we want to measure environmental impacts, we need a method that not only looks at some situations or processes, but a method that looks behind the scenes and considers the entire life cycle with all the upstream processes and all the downstream processes. And we need a method that also considers a large number of environmental impacts, not only the carbon footprint, but also other impacts such as land use change or acidification, eutrophication, toxicity, and so on. And we need a method that is based on scientific evidence as far as possible and that can quantify the environmental impacts with these indicators. And life cycle assessment fulfills all these tasks. We can then analyze the hotspot, the environmental hotspot of a product along the process chain, or of course we can also compare different products or different measurements from an environmental perspective. Now, how is an LCA done? First of all, we collect data and create the process system. In this case, it's for paper, but this would look similar for bioplastics or some other plastics. And all these processes use resources and emit some emissions. And what we do in LCA, we sum up all these emissions, and in the end, we have calculated all the different emissions of the total product system, and this is a list of about 500 or 700 different emissions and resources, and then we further categorize these emissions to the different impact categories. We know that carbon dioxide adds to global warming. The same is true for methane, for example, and NOx does not contribute to global warming, but NOx then does contribute to acidification or eutrophication. So after this step, we have the results for the different environmental impacts. There are about 16 environmental impacts we can calculate at the moment with LCAs. And then we can go a step further or 2 steps further and aggregate and weight these different impacts to the so-called single scores, to the total environmental impact. If we look at the ISO norm 1440 and 44 about LCA, it is only allowed to publish the midpoints, as we call it, that all these different environmental impacts if this study is disclosed to the public, and it is not allowed to do any further weighting to the single score. However, this further weighting is of high value for decision support, and I'd like to show you why. In a study, we once compared PET bottle with an aluminum can, and with regard to the ISO norm, these are the results that you are allowed to publish or to describe. And you see there are many different results here available. And the problem is, if you have to do a decision, shall I use now the PET bottle or the aluminum can for my packaging? Which one should I take? And as a commissioner, you have now several options. You can do an equal weighting, just weight all the different impacts in an equal way, and then you just do some sort of ranking. Or what many do, they choose a specific impact that they think is very important, such as climate change. Or the third option you have, you just hand back the study and say, come on, I have to do a decision. Tell me which one is the better option from an environmental perspective. And what we then do, we use this weighting schemes that are well established and calculate the single score. And you see there is a difference in the conclusion. With regard to climate change, the PET bottle performs worse than the aluminum can, but with regard to the total environmental impact, it's exactly the other way around. So it's very important that we do not only look at climate change, but at all the different impacts and try to weight them. And this is especially important for biopolymers. The two most important methods we use normally is the ecological scarcity method. It's a Swiss method, and this is based on a distance to target approach. So for all the different emissions and resources, the method looks at the actual flow in a certain region and the flow, the critical flow, the flow that should not be exceeded. And this difference then defines the eco factor of all the different emissions. Then the other method is the environmental footprint version 3 method. This is a completely different approach. First of all, the 16 environmental impacts are calculated based on the state-of-the-art models. And then there is also a normalization and weighting step involved in this method so that we are able to calculate the total environmental footprint or this single score. Now, with regard to biopolymers, there are like two groups of biopolymers. The one that is based on renewable resources that can be degradable, such as PLA, but that sometimes are not degradable, such as BioPE or BioPET. And then there is a second group of biopolymers, which are biodegradable, and some are not based on renewable resources, but based on petrochemical resources, such as the PBAT or PBS. And in the coming slides, I'd like to address these two groups and have a look at the renewability and is there an ecological benefit of the renewability, and the same for the biodegradability. The renewable resource does not have to be an advantage per se. as you can see here in this slide or in the coming slides. And we did once a study about 12 different biopolymers. Most of them were first generation biopolymers. And what we saw is that most of them show the advantage if we look at climate change or fossil depletion, such as the bio-based PE in this result here. But others didn't even show an advantage in climate change or fossil depletion, such as the potato starch blend here. And this was due to the rather low-scale production and lower efficiency in the energy use, fossil energy use, and material use and wastes. Now, if we look at other impacts, we also have higher results with regard to human toxicity or freshwater eutrophication, in this case, even for bio-based polyethylene. And so if we look at the total environmental impact, if we weight all these different impacts we have, we then see that, or we saw in this study, that most of the first generation biopolymers showed a higher total environmental impact, or maybe sometimes a similar one if we look at also at the uncertainties that are involved, but we didn't see any first generation biopolymer that had a lower environmental impact than the fossil polymers. And why is that? If we, for example, need corn as a source for a biopolymer, we first have to prepare the field, then we have to add fertilizers, we need some pesticides, and in the end, we harvest the crop. And there is a lot of fossil diesel involved in this step, and we also need a lot of synthetic materials such as pesticides or also mineral fertilizers. So you see here it already that cannot be carbon neutral. We have a lot of impact here already. Then the crop is transported to the biopolymer facility. Again, we need energy and chemicals. It is further transported to the final production of the product, in this case a cup. And then after the use phase, this cup is then disposed of in an incineration plant, or in this case in a compost facility. If we look at the impacts along the process chain, most of the impact of this first generation biopolymers comes from the cultivation phase. It's this yellow-green bar. We don't have that if we have a fossil polyethylene. Of course, the oil also needs to be extracted and refined. This is all included here in this purple or violet bar. And what we see, the advantage of the bio-based PE is that in the final disposal, in this case incineration, we have almost no impact, because the carbon included in the material is so-called biogenic and therefore not accounted if it is burned again. Whereas for the fossil polyethylene, we then have a lot of carbon emissions into the air. So what if we could cut this agricultural phase? And this is the case if we have this so-called second generation biopolymers based on waste or residues. In this study, we looked at 3 different second generation polymers, and they all showed the same result. They were actually better from an environmental perspective than the fossil-based alternative. And not only for climate change, but also for the total environmental impact, because this, as a waste, it comes into the system with a burden-free. So there is no upstream impact involved in the waste. And this is the big advantage from an environmental perspective. Now, with regard to the biodegradability of plastics, we once did a study about different biopolymers and other materials that are degradable that you also can just buy in the supermarket. And we compared 3 scenarios: the incineration in Switzerland, the anaerobic digestion, where we actually did methane measurements. We measured the methane potential of the different materials and gave then also credit for this, for the replacement of the natural gas. And we also looked at composting. And cellulose acetate was one of the biopolymers with the highest methane potential. That's why I'm showing here this result. With regard to incineration, we gave a credit for the electricity and heat production in the incineration plant. In the anaerobic digestion, we have this methane that replaces natural gas on the market. And with regard to composting, there is no benefit or no credit because there is no nutrient involved in a biopolymer. So we don't have a credit for fertilizer replacement. And these biopolymers often degrade over time to carbon dioxide and other short molecules, but they do not add for organic matter or humus. So we cannot give a credit there. The picture looks completely different if we look at a palm leaf, for example, or other biomass. Here we have in the anaerobic digestion, besides the methane potential, we have some credit for the nutrients involved because the digestate is then afterwards applied to a field, and there you can replace some fertilizers, and it also adds to organic matter and humus, and this is quite a huge credit. The same is true for composting, so it makes sense to degrade biomass such as palm leaf in an anaerobic digestion plant or composting plant, but it does not really make sense to degrade these biopolymers in an anaerobic digestion plant or especially in a composting plant because you have a higher advantage or a higher benefit if you add these biopolymers directly into an incineration plant. So yes, these biopolymers, they are renewable and or biodegradable, and they often show a better carbon footprint than fossil plastics. And if they're made from bioproducts or waste, if the so-called second generation biopolymers, they have a lower environmental impact. But they are not climate neutral, these biopolymers. They are not produced without fossil resources and normally not more environmentally friendly than fossil plastics if they are produced with agricultural crops or if they are so-called first generation biopolymers. And the degradability has no added value compared to incineration. But always be careful with simple rules. To say biodegradability has no advantage is not true in every case. If we have additional benefits, such as the dissolving of drug capsules in the body, or also if we have less micro and macro plastic in the water or in the soil in countries with insufficient waste management systems, if we use biopolymers, then these characteristics can have environmental benefits. We did not address this sort of benefits in our LCA study because we had, as a scope, we had, or system boundary, we had Switzerland or maybe Germany, where we have good waste management systems, but in Asia, for example, this is a completely different picture. In one of my last slides, I'd like to show you also the impact or the benefit of recycling, also compared a little bit with biopolymers production. In the result, in the figure on the left side, you see a bottle produced with fossil polyethylene and with no recycling. So this is completely incinerated and burned. And this leads to an impact of about 300 eco points per 1 liter bottle. If we produce the same bottle based on fossil polyethylene, but then we have a recycling system and 80% of this bottle is recycled in average, then we can reduce the impact substantially to about 200 points. And I forgot to mention, we calculated this results with the circular footprint formula. This is an approach especially designed for packaging materials to include recycling benefits after the use phase in a way so that you have a fair comparison between different materials. I will not go into details regarding the circular footprint formula, but there is also some information available in the web. Now, if we use a first generation bottle instead of a fossil polyethylene, we have a higher impact, even though we would collect it and recycle it, but the impact is still higher than the fossil PE bottle that is not recycled at all. And what we also see, if we use a second generation biopolyethylene or also a recycled material, then we can reduce the impact furthermore. So it makes sense to recycle, it makes sense to have a recycling system, but it also makes sense to use the second generation biopolyethylene and just look that you can then recycle it after the use phase as well. So we would have the optimum case. So I'm already at the slide with the conclusions. Biopolymers based on crops, these first generation biopolymers rarely show a better environmental performance than fossil polymers. The second generation biopolymers often show a better environmental performance, so it makes sense to use them. And we also have seen that the biodegradability itself is not an environmental advantage per se. And we have also seen the secondary polymers, so these recycled polymers, show a better impact than fossil polymers and a similar impact to second generation polymers. Thank you a lot for your attention, and I'm happy to answer your questions now.
Thank you very much for the exciting presentation, Thomas Kegi from Carbotech AG. And now we turn again to our guest. Welcome, very warm welcome from us. Hello, Thomas Kegi, how are you today?
I'm fine, thank you. I'm happy to be in this virtual meeting, and I'm looking forward to the questions.
Okay, so I have already a question for you from the chat. The listeners would like to know, what database have you used for your LCA?
As a background database, we normally use the eConvent database version. Well, it depends on the study I showed. It's about version 3.5 to 3.8. And we normally use the CIMA Pro software to calculate the LCA. The foreground data we normally collect. So that means that we ask our clients, what is the weight of your biopolymer, what kind of materials is involved, what is the energy use, and so on. For the background information, we use the eConvent database.
Hello, also from my side. Then is the next question coming in. Is it hard to get the needed data?
Oh, yes.
Okay, that was a good question.
Again, it really depends on the study, but let me put it this way. If our client is the biopolymer producer, it's quite easy to get the data because they know the data. But in this study where we looked at 12 different biopolymers, our client was not a producer of biopolymer. It was someone who wanted to know, shall we use biopolymers for packaging materials or not? And so we had to ask 12 different biopolymer producers, and we had to sign 12 different NDAs, and we had to really fight for each data point to get and to collect. So it's sometimes hard to collect the data, and that's also then often the case why this sort of study is not published or not public, because it's confidential. So it is, well, you won't find it on the internet, and that's really a shame. It would be nice to share more knowledge, but most of these sort of studies are then just confidential. That was what I was looking for.
Okay. And how long does a LCA take to be done? Another question from the chat.
Again, it depends what kind of LCA you do. We have like 3 different sort of LCAs. A screening LCA, which can be done very shortly and quickly, until the full LCA study that sometimes takes some months. And the most critical time issue is always the data collection phase. So we prepare some sort of data collection table, and then our client or this company who should give us the data has to fill in this data, and sometimes they need some weeks to fill in this data. So this is the most important step, and after that we need sometimes 1 month or 2 months to finish the study. So it's about, let's say, 2 weeks quickest to half a year or 1 year.
Okay, that's a long time though.
Okay, there's another question coming in.
Yes,
Julita,
yes,
that's your
sure.
turn.
Of course, we have lots of questions, which is good. So avoidance of microplastic is a big benefit of biodegradable biopolymers. How can this be covered?
It's a very good question and a tough topic, because most LCA methods or impact assessment methods are not able to cover this topic. We cannot calculate the environmental impact, micro or macro plastic. The only method that tries to do that is ecological scarcity, the latest version, the version 2021, which has an eco factor for microplastic to soil and water. But normally it's methods you cannot do that, and it's so far not really known how damaging this sort of microplastic actually is. And this is the problem. This is the reason why we cannot really calculate the impact with most methods. I also think microplastic can have is a very important issue, and there needs to be further research done to address that better.
Okay. So, okay, then now we have a good overview. And interesting was also the statement in your lecture that recycling will be a key issue in the whole LCA topic. So that means also biopolymers can be recycled. So this may be a further benefit of the environmental benefit for biopolymers. Okay.
Thank you very much for answering the questions and for the insights, Thomas Kegi from Carbotech AG. Thank you for being with us.
Thank you.